Right, the 2013 electricity level 3 physics paper, and the first question is on capacitors. The circuit below can be used to produce a flash of light from a lamp with a fixed resistance of 128 ohms. So there's that 128 ohms there, and we've got the internal resistance to be considered. Switch 1 is closed, there's switch 1 there, and the capacitor charges up. So the lamp's not in the circuit when switch 1 is closed. Calculate the charge stored in the capacitor when it's fully charged. You can use the equation Q equals CV, and that will give you the solution. Your voltage in there, that's the one little trick I guess, the voltage can be the 12 volts, because even though when there's current flowing that there'll be a small voltage drop across the internal resistance, there's no voltage drop across the internal resistance when there's no current flowing, which is when it is fully charged. Otherwise it wouldn't be. So it has to go up to 12 volts across there. Carrying on, B, the internal resistance of the battery is 1.80 ohms. Explain why the charging is almost instantaneous. If you do your time constant calculation, T equals RC, you'll see that's a very low time constant. And remember, it's roughly 3 to 5, you can say 5 to be on the safe side, time constants. Before we would consider a capacitor fully charged. And so the time it takes to become fully charged, 5 time constants, is very low. Now switch 1 is opened, so the battery is disconnected from it, and switch 2 is closed, so the capacitor is just going through the lamp. The capacitor is like a battery in the lamp, but there's no internal resistance with the capacitor. There would be resistance in the wires, but we don't consider that. C, on the graph below, mark values on the axes and plot a curve with at least 3 points. Oh, I'm on the wrong tool. 3 points to show how the charge and the capacitor changes during the discharge process. Usually you see graphs of voltage against time. We're not doing that, it's charge against time, but from what we would know as a capacitor is discharging, the charge stored on it is directly proportional to the voltage, so as the charge disappears, so does the voltage lowers. But you can use Q equals, we got that charge initially at the start and with the first calculation, so you just put that charge at your first point. I think it's 1.5 millicoulombs or microcoulombs or something like that. You can go check yourself. But then after it'll have dropped to after one time constant to 63. That drop will be 63%, and then the remaining 37% there. So 0.37 times that initial value if it was 1.5 millicoulombs or something like that. Anyway, and what do we have to have? 3 points to show, so you'd have to have 1, 2, 3 time constants, trying to get the spacing between them even. I'm doing it very rough on here for the purpose of explaining. Plot your points, plot it really carefully, smooth curve through. Good way to draw a smooth curve is to look at the point that you're about to draw through and just draw towards it, and your finger tends to follow where you're looking, which is quite a nice little tip. D. The lamp will glow at normal brightness if the voltage across it is between 9 and 12 volts. So 12 volts is the maximum, which it would start off with, and it's going to drop, and at some point it'll drop below that 9 volt value. Use the graph to estimate the length of time that the lamp is glowing at its normal brightness. Okay, so we have to find the charge level, since our graph is in charge, using Q equals CV. We know our capacitance, that's given to us earlier. Excuse me, and our voltage is going to be 9 volts, because that's the charge we're looking at, not Q, 9.0 volts, because that's going to give us that lower point, and when it drops below there, we need to read the time off of our graph to give that. Okay, so you can follow that one through. You find that Q value, look on the graph to see where it is, and let's just come up there so we can look at that. So you've calculated that Q value in red there. It might be, say, here, and then you look to that time, and that's the time that it's going to take before it drops below that value. And that's the length of time that the lamp is glowing at its normal brightness. You always have to go back to that question and make sure that you're answering exactly what it says. E. Second identical capacitor is connected in series with the one shown. Show that the total capacitance of the two capacitors is this. So you're just adding two capacitors in series, but remember when you add them in series, you use the resistance parallel formula, if you know what I mean. So 1 over C1 plus 1 over C2, You take all of that and you do the inverse, and that'll give you the capacitance for that part. And in this case, remember, it should be lower because you're adding them in series, reducing the amount of charge that can be stored on the plates. Okay, moving down to F, and I think that actually asks about this. Explain using physical principles, so physical principles, not formulas, the effect of the new capacitor arrangement on the time constant of the circuit. And I think I've already kind of covered that, but the time constant has to drop since the overall capacitance, the total capacitance drops, and less charge can be stored, so your charge that can be stored drops, therefore it takes less time for that charge to flow off the plates. And therefore it's going to be a smaller time constant. I think that's clear enough.